we've gone from looking at the 4-stage model in our basic computers to looking at CPU and what goes on in the CPU, and then having a look at all these zeros and ones and bits and bytes that we've spoken about. So how do all these things come together and actually do the particular trick? Well, let's go back to the old days and start from where we were. We're going to have a look at vacuum tubes, transistors, then we're going to look at semiconductors, and we're going to have a look at the different generations of computer. Then we're going to finally have a look at logic gates, what they are and how they work. So let's start off with, in the old days, how do we use switches? How do we create switches? Well, we use things called valves. And they were valves or vacuum tubes, and they were introduced in the early 1900s. And they were used as switches. They were big, and that's why our computers were really big. And you can see what they look like, and these are just some small examples. And this is why some of the earlier computers took up not just rooms, but whole floors of buildings, because we had to put a lot of these together to make them work. And these things work because they were called vacuum tubes, because if you apply electric charge and you try another electric charge, it will create a vacuum, which then allows the spark to jump, and we have a connection and we have a switch. And that's what it is, just an on-off switch. We don't have a current, it's off, we have a current, it's on. And so these things work together. And you know, these big computers in the old days couldn't do very much and took up lots of space. And I guess that's where bugs came in. You often hear about computer programmers talking about their programs having bugs. Where did it come from? Well, in those days, we did have actual bugs on there, moths that would fly in because of the light they could see, and they would mess up some of the electronics in there, and the programmers or the technicians had to actually go in there and pull the bugs out. Hence the reason why things are called bugs. But there you go, just something a little interesting. But then around about the 60s, transistors came along. And transistors were smaller switches, which got smaller and smaller. And it's an electric component with 3 pins. And it's a switch like the others. So if we've got a charge between 2 of the pins, the collector and the emitter, will depend whether we've got a switch that goes on or off. And it's operated by having a small current in the 3rd pin called the base. So if we had a current going through there, we'd have a switch on. If we didn't, we'd have the switch off. So these were transistors, smaller versions of these valves. So everything became smaller. And the big thing in those days was transistor radios, and how instead of having big sideboards that were radios, we now put them all down into a really, really small space and called them transistor radios, really tiny. And then we moved on to integrated circuits. Because of the way we learned to work with silicon chips, we call them semiconductors. And what does that mean? Well, it means sometimes they conduct electricity, sometimes they don't. And because of the chemicals we put in there, if we apply a charge on what used to be the pin on the transistor, we apply a charge through it, it will allow the current to go through. If the charge didn't go on it, we wouldn't have a current going through. So again, it's a switch, but it's a very small switch. And you have many of these on the chip or the microchips. So it's a set of electronic circuits on one small flat piece or chip of semiconductor. And that semiconductor is normally silicon. And the good thing about these, it allowed the integration of a large numbers of tiny transistors into a small chip. So things shrunk even more. It resulted in circuits that are smaller, cheaper and faster. And so therefore, computers became smaller. So instead of being in the big rooms, they were maybe just big machines now. And then we moved on to microprocessors. And a computer processor, which incorporates the functions of all of a computer's central processing unit in a single integrated circuit, or a few at most, was called a microprocessor. And the multi-purpose, clock-driven, register-based, we've spoken about before, digitally integrated circuit. It accepts binary data as input, processes it according to the instructions stored in its memory on the chip itself, and provides results as outputs. So these chips came with instructions burnt in on them, already on there. And depending on the sequence of zeros and ones that were sent through, it will know what to do with those zeros and ones, whether to process it, whether it was data, and then how to output it as well. But things shrunk and have kept shrinking all the time. And we'll have a look at Moore's Law a little bit later on. So if we say there are 5 generations of computers, let's go through all the different generations and why they're so different. So our first generation of computers, obviously vacuum tubes, and these were based around the 1950s, and these were called valves or precursors of, these were the precursors of transistors. But bulbs were very bulky, a bit like electric bulbs, and they produced a lot of heat. So things would go wrong quite often. You know, installations used to fuse and all sorts of things used to happen, bugs in the system, etc. And how did we put information in and out? Well, we used punch cards, paper tape and magnetic tapes, and they were used as input and outputs. And the thing about these punch cards, as I remember, you had to put them all in a sequence, and the holes or no holes represented a byte. The only problem is you'd spend hours putting the program together, and then all you had to do was go over and trip over and the whole thing fall over, and you had to start all over again. What a pain. So first generation of computers programmed using machine code, i.e. information that directly in zeros and ones using these punch cards. They were very expensive and they were very large. You couldn't have one of these on your desks, and only the big, large organizations could actually afford to use them. So when we come to second generation, we now move down to transistors, and these would be in the early 1960s. Transistors replaced the vacuum tubes of our first generation computers. So all of a sudden, things became cheaper. Less power was consumed. Things became smaller, more compact in size, and they were more reliable and faster. More transistors could be used to make more complex computers. We still use magnetic tape and magnetic discs, we use magnetic discs now as secondary storage, as well as punch tapes, which are still being used. And it was about this time that we started using assembly language, high-level programming languages such as Fortran, COBOL and ALGOL. So these were the early generations of languages on these machines. And then we move on to the third generation computers, and these were our integrated circuits. And these were introduced in the second half of the 60s. And integrated circuits really was the start of our third generation computing. And integrated circuits have many transistors, resistors and capacitors, along with all the associated circuitry that goes with it. So again, you know, it made computers smaller in size, it made them more reliable, and it made them more efficient. And the type of high-level languages, although we still use assembly language in some cases, we had Fortran, COBOL, Pascal, BASIC, which is where I started, and ALGOL, and a few others as well. So, you know, this third generation became a bit faster and it became smaller. And then we move on to the fourth generation computers, which were where our microprocessors came in. And this started around the 1970s, and they used very large scale integrated circuits. And these very large scale integrated circuits have upwards about 5,000 transistors on a single chip, which we called a microprocessor. But it was still only 5,000. And of course, computers became more powerful, more compact, more reliable, and quite importantly, more affordable. And this is really where our personal computer revolution began. This is where computers started appearing on people's desks. Although there is the story of the director of IBM, who were really into creating these computers, the early PCs, who said, who's going to need a computer on their desk? Well, we don't all get it right, do we? And now we come to the fifth generation, and that's where we are now, from 1980 to date. And we use what we call ultra large scale integration. Not very large scale integration, but ultra large scale integration technology, which basically means these chips can have upwards of 10 million electronic components. But if you compare that to one of Apple's latest chips called the M, it's decided to move away from ARM and create its own chip so it didn't have to rely on anybody else. We're talking about 28 million electronic components. And this is where our object-oriented languages started coming in, because we wanted to be able to make coding more efficient. We had the room to do that, we had more memory, more power, and so this is where our object-oriented languages, starting off with C++ and then Java and C#. And that's where we are at the moment. What's the next generation? Who knows? A lot of people are now talking about quantum computing. Maybe. We'll wait and see. We can always look back at Moore's law. And Moore was actually said, he used to work for, I think it was IBM, and he came up, which he said the rate at which transistor counts have increased over the last few years follow a particular pattern. And the pattern was that the transistor count doubles approximately from every 18 months to 2 years. So in 2016, a single chip processor transistor count was 7.2 billion in the largest commercially available chips. Switch on to 2019, and now we've gone to 39.54 billion, and we use the term MOSFETs, which is metal oxide semiconductor field transistors, or MOS transistors, and now we go to 2020 and we're looking at 54 billion MOSFETs. So things get bigger and bigger. When were they going to stop? Never. Things are just going to get bigger all the time. And if you have a look at Moore's law on the graph on there, you can go and find that at this particular web page and have a look at it in more detail yourself. But things are still moving very, very quickly. So that's our processors. That's where the pedal hits the metal, as it were, because it's these switches that give us the on or off. But then how do we process these zeros and ones? How does having switches allow us to process? Well, we've already spoken about bits and bytes and how we send things in as a byte, computer word, as 8 bits. So what happens to these things as they go through? If we have a look at here, if you talk about a basic transistor and how it works, we've said there's a switch. So if we have some current coming in, and then current coming in from the other side, current flows through. If we apply a current on the other side, then it stops the current from flowing through. So we either have a current coming through or we don't. And now with semiconductors, we found a way of doing that. So if we actually put the current on 2 places, we won't get the current coming through. I'm going to introduce you now to logic gates. And logic gates is where really the area of thought and being able to plan your code and functional decomposition and all that hits the actual physical elements. And so what are gates? Well, we can actually put these things together in things called gates, and not Bill Gates. So as an example here, we've got a little diagram here which shows us something called an AND gate. So what does an AND gate do? Well, if I have 2 areas, or 2 nodes where my bytes are coming through, then as each one goes through, what I have to make sure is if this one's on and this one's on, then I get one coming through the other side. If this one's off and this one's on, nothing happens. If this one's on and this one's off, nothing happens. If this one's off and this one's off, nothing happens. So AND will only send a signal through if both are positive, or both currents coming on both sides. And you can see that in the table over here in the diagram. As we feed through that byte, we get a different byte coming out the other end. It's transformed because we're using binary addition, a binary AND to create those there. And you can see how that's created below on the diagram. So we can see here that the flow's coming through, and as it comes through, if we have two ones coming through, we'll get a 1 at the other side. Anything else will give us a 0. And then we can see the table at the bottom that gives us the result. So that's a very basic gate, but there are 7 different types of gates that we can use. We've looked at the AND, and we've looked at we've got 2 inputs, and then we can look at the results that we've got over here on the table. So that table shows you what happens as we pass a binary digit through. Then we have the NOT, which is known as an inverter. And what does that do? Well, that just simply switches it around. So if I have a current coming through, I don't have a current on the other side. If I don't have a current coming through, I have a current coming through. So a 1 will give me a 0, and a 0 will give me a 1. Then I have a NAND gate, which is a combination of the NOT and the AND. Okay, and as you can see with this one, if I don't have anything coming through either one or the other, then it knots it, it reverts it, and it sends me a 1 through. If I have a 0 and a 1 coming through, then it allows me to go through, because basically it just reverses everything that the AND gate will do. So the only time I won't get a current coming through is if both currents coming through and both are 1. The other one we've got is an OR gate, and the OR gate is slightly different, well, very different from the AND gate, because the OR gate will allow a current to go through if I have a 1 on one side and 1 on the other, or 1 on both sides. So if you look at the table over there, if I have 2 zeros coming through, I don't have a current coming through. But if I have any other combination, it will actually give me a current coming through. So this one, or both. And then we apply the same to a NOR, which basically is an OR, not an exclusively OR, an OR, but the NOR reverses. So if I have nothing coming through, 0, 0, I get 1 as an output. If I have a 0 or a 1, a 0 and a 1, then as an OR gate that would send me a signal through, but because it's a NOR gate, it reverses that and gives me a 0. And it'll give me a 0 for any other combination as well. So the only time I'll get any current coming through is if there's nothing coming through either of those inputs. And then we look at the exclusively OR gate. Now we've seen the OR gate and we said it's this one or both. The exclusively OR says that only if we have 1 from here or 1 from here. So only if I have a 1 on one side or a 1 on the other side. If I get 2 together or nothing comes through. And you can see that on the table as well. And then finally, we've got an exclusively not OR, an XNOR, okay? And this one basically takes the exclusive OR, which if you remember will only send the current through if I've got 1 and a 0 or a 0 and a 1, and it turns that around. So basically now, if I have no input coming in, no charge coming through, 0, 0, I get 1 coming through. If you have a 0 and a 1, then no current comes through. If I have a 1 and a 0, no current comes through. But if I get 2 ones coming through, then I'll get a 1 come through. So what do all these do? What are these gates all about? Well, it's the process by how we allow the actual switches and the power to flow through. And depending on how we combine these, we can make our processor perform certain actions. And you can have a go at these. If you have a look at the website that we're going to show you on here now, you can have a go around and play around and connect all these things together to see how they work. Okay, so let's have a look at how a calculator will work with gates. And you'll see we've got 3 gates, an exclusive OR, an AND and a NOR. Remember, the AND needs 2 signals to go through to make a connection. The NOR will reverse any OR, and the exclusively OR needs only 1 coming from each side. So let's start off first of all, and we'll start off with 2 switches that are off. And what you're going to see is no signal coming through. So if there's no signal coming through when we start our machine, then you're going to see that no signal there, and it's only going to be picked up by the NOR gate, because the NOR gate reverses an OR, and since there's nothing coming through, we'll get the light coming up to give us a 0. That's 2 off switches. Then when we switch one of the switches on, the top one, you'll see the signal coming along on the blue line, and you'll see no signal from the red line, and the only one that will catch that will be the exclusively OR, because an exclusive OR needs 1 or 0 and 1. So the answer will be 1. And the same thing happens again when we look at the other side, because we only have one charge coming through, and that's now going to be on the red line because we switched it around. And again, the same thing's going to happen. It's going to be caught by the exclusively OR gate, not the other 2, and the light bulb will go up for 1. So we've done 1 and we've done 0. The only one we've got left is 2. When we have 2 charges coming through on both the lines, It obviously meets the needs of the AND gate because we have 1 on both sides coming in, which will then give us an electronic impulse coming through, which gives us the answer for 2. And that's how we can do a calculator using logical gates.